Funding for this program was provided by the Annenberg CPB project.
Additional funding provided by the people of Dow, the company that lets you do great things. The 8,000 scientists of the Eastman Kodak Company. The Exxon Education Foundation on behalf of Exxon scientists. And
the chemical we're most familiar with is the strangest substance on Earth. It forms solutions that can dissolve solid rock, yet it's gentle enough to saturate the tissues of every living thing. Its molecular mass is less than most of the gases in air, yet it's normally a liquid dense enough to float a tanker. It's extremely rare on every other planet in the solar system, yet it's one of the commonest compounds on Earth. It's water, and it's the strangest chemical of all. There's so much water around us, we take its unusual characteristics for granted. In fact, water's oddest trait is the one that's most familiar. It's a liquid at normal temperatures. The presence of a large amount of liquid water has had a profound effect on planet Earth. Constantly circulating masses of water moderate extremes of temperature and make the planet livable. In plants, water reacts with carbon dioxide to form glucose, the source of energy for all life. Water dissolves so many things, it's called the universal solvent. Plants are 95% water, fish 80%, and humans 65%. So all living things need a continuous supply. Because of water's unique characteristics, we put it to plenty of other uses. In fact, we use it far more than any other substance on Earth. The annual consumption in the U.S. for all purposes is 2 million gallons per person. 80% of the world's water is used in agriculture. In industry, we use it to transfer heat and as a chemical reactant and solvent. But remarkable properties can create difficulties. Because it's a liquid, water can pick up large amounts of contaminating particles. And since it's a good solvent, it can dissolve potentially harmful chemicals. As the Earth's population grows, we add more and more contaminants from industry, human waste, and sediment runoff. A major challenge facing the world of chemistry is to find better ways to clean up the water that we use, and more efficient ways to use the water that we have. To do that, we must first understand the chemistry behind the odd behavior of this unusual substance.
My friends know that I'm the kind of guy who always carries around molecules in his backpack. You never know when they might come in handy. Here, for instance, is a nitrogen molecule, one component of the atmosphere. It's got a molecular mass of 28 grams per mole. Now, here is an oxygen molecule, the more important component to us of the atmosphere. It has a molecular mass of 32 grams per mole. Let's see what else I've got. Carbon dioxide, the molecule we exhale. It's a bit heavier, but still a light gas with a molecular mass of 44 grams per mole. But here is a molecule which has a molecular mass of only 18 grams per mole. It's water. It's lighter than any of these other molecules which are gases, and yet as you know, it's not a gas. It's a liquid. What is it that makes water so special? It can't be just the atoms in it, oxygen and hydrogen, because we have other molecules which contain those atoms and which don't have the properties of water. It must be the special combination of the atoms with each other, their arrangement in space, the disposition of the electrons in them, which gives this molecule that is so important to us, its special properties.
Water molecules are polar. Oxygen has a much stronger attraction for electrons than hydrogen does. So the electrons in each bond spend more time near the oxygen atom than they do near the hydrogen atoms. The oxygen atom, with 2 pairs of unbonded electrons, carries a partial negative charge. The 2 hydrogen atoms carry a partial positive charge. Each positive charge is concentrated in a tiny exposed hydrogen nucleus. When a positive hydrogen nucleus of one molecule comes near the negative pole of another molecule, they're attracted to each other. This attraction forms a hydrogen bond. Hydrogen bonds between molecules are not as strong as the covalent bonds that hold molecules together. But it takes far more energy to break apart molecules held by hydrogen bonds than to separate other molecules of similar size and mass. Below 0 degrees Celsius, hydrogen bonds lock water molecules together into solid ice. As the temperature rises to 0, molecular motion increases and some of the hydrogen bonds are broken. Groups of molecules slide over each other and the solid form becomes a liquid. It remains a liquid over a wide temperature range. At 100 degrees Celsius, molecular motion becomes so rapid that the hydrogen bonds are broken completely. The molecules fly off and become a gas. Water occurs as a gas at the same time it's found in both the liquid and solid states. That's fortunate for us, because if some of the water on Earth didn't evaporate into a gas, it wouldn't rain or snow. And we depend on rain and snow to replenish the fresh water needed for drinking, agriculture, and industry. Although water's found nearly everywhere on Earth, 97% of it is a salt solution. Less than 1% is fresh water we can use. Most fresh water is locked up in glaciers and Arctic ice caps. But ice does provide one benefit. It floats and insulates the water underneath from freezing. Ice floats because of another of water's unusual properties. The solid form is lighter than the liquid. If ice were heavier than liquid water, it would sink and stay frozen. Most of the water on Earth would turn solid, with drastic consequences for all life.
Water is a constant part of our lives. We're taking it in all day long. We take water to extract tea from tea leaves. And coffee. Coffee is extracted from coffee beans. And soft drinks and hard drinks, they're really just water solutions. Fruits and vegetables are just about all water. Let me show you. Take this orange and cut it. You can see the juice in there. Lots of water in fruits and vegetables in there for sure. And we use water for cleaning and certainly for cooking. Now I want to show you something. Bring this glass in here. And take a cube and drop it in there. Wow! Now this is water. See the ice floating? Look what happened here. Have you ever seen solid sink to the bottom like that? Looks pretty bizarre, doesn't it?
The liquid on the left is an organic solvent. A frozen cube of it sinks because the solid form is denser than the liquid.
When substances cool, when they get colder, the molecules slow down. And they get closer together. They pull in closer together. So the solid is more dense than the liquid. And so the cube should sink in its own liquid. But water doesn't act this way. As it freezes, it becomes less dense. It expands. Let me show you some proof of that. A full bottle of water put in the freezer will break. Why? Well, as water goes from the liquid to the solid, it expands. Now, this is the only substance I can think of that does this.
As water's temperature decreases, its molecules slow down and begin to form additional hydrogen bonds. As they lock together, the molecules orient themselves farther apart than they were in the liquid state. They form a six-sided open pattern, a solid. The solid, ice, is less dense than the liquid. So, ice floats on liquid water. Frozen water molecules form the most beautiful shapes, snowflakes. Snowflakes condense directly from water vapor in the air at below freezing temperatures. Making snowflakes is big business. Ski resorts around the world depend on snowmaking machines to keep the slopes covered when nature fails. Until recently, the temperature had to be below freezing to make artificial snow. But a technology has been developed to make snow at several degrees above freezing. It's called the SnowMax process. A protein from bacteria helps to arrange water molecules into ice. Under the microscope, crystals take shape as the protein makes it easier for hydrogen bonds to lock the molecules together. On the ski slopes, freeze-dried bacteria are added to water that goes into snowmaking machines, and fluffy white crystals come out. Frozen water is relatively pure, even ice from frozen salt water. When water molecules link together to form ice crystals, they leave other substances behind. Rainwater is also relatively pure. When water molecules evaporate into a gas, they leave behind whatever was dissolved in them. But even raindrops contain dissolved gases absorbed from the air. They also pick up dust particles on their way down. And once they hit the ground, they pick up much more. Water requires a lot of dissolved material, organic compounds from plants and animals, and inorganic minerals. These substances dissolve in water as individual molecules or ions. That is, they form solutions. Water's unique ability to dissolve many different substances is due to its polarity and its ability to form hydrogen bonds. We can represent water molecules in a more compact form to show how they dissolve sodium chloride. Ionic compounds such as sodium chloride consist of alternating positive and negative ions. Water's relatively positive hydrogen atoms attach to the negative chloride ions and pull them out of the crystal. And the relatively negative oxygen atoms attach to the positive sodium ions and pull them out of the crystal. The forces of water's attraction are stronger than the forces holding the sodium chloride ions together. When all ions have been pulled out of the crystal, the salt is dissolved. It's in solution with water.
Now here I already have a solution, liquor. It's a solution of ethyl alcohol and water. It's 80 proof. That means 40% alcohol and 60% water. Now how does alcohol dissolve in water?
Water molecules are polar and form hydrogen bonds. Ethyl alcohol molecules are also polar, and they also form hydrogen bonds. When ethyl alcohol mixes with water, it dissolves. The opposing poles of alcohol and water are attracted to each other. And the water and alcohol molecules also form hydrogen bonds with each other.
Water is called the universal solvent because so many things dissolve in it. But there are some substances that do not dissolve in water. Look what happens here. If I pour water into this liquid, Watch what happens. There's 2 layers. And no matter how much I shake it, they still don't mix. They'll separate back out to those same 2 layers that's in there. Now, how come? Well, the water is composed of polar molecules, whereas the other liquid is composed of nonpolar molecules of relatively high molecular weight. And because these 2 liquids are not alike, they won't mix.
Water dissolves molecular substances that resemble it in size, polarity, and hydrogen bonding ability. Larger, nonpolar molecules that don't form hydrogen bonds are insoluble in water. An insoluble liquid mixed with water stays in a separate layer. Chemists have learned how to make such molecules soluble by adding ionic or polar portions to them. They can now make brand new water-based products out of normally insoluble molecules. It's a technique used to modify natural polymers, long chains made of smaller molecules linked together. Dr. George Broad directs water-soluble polymer research for Union Carbide.
We come in contact with the results of water-soluble polymers every day of our lives. For example, a latex paint that you use on your house or to coat your walls. The stability of that depends on a water-soluble polymer. Personal care and medical products that are essential to us every day are based on water-soluble polymers.
Dr. Broad has modified cellulose, plant fiber, so it will dissolve in water. The water-soluble cellulose is made into a gel that's used to open up clogged formations in oil wells. He's also figured out a way to take chitin, the polymer in crab shells, and make it dissolve in water. Potential uses for soluble chitin include surgical sutures and blood anticoagulants. Water's solvent ability lets it dissolve a wide range of molecules, whether we want it to or not. It can dissolve minerals and pick up calcium, magnesium, and iron ions. They're responsible for the hard water that tastes bad, reacts with soap to form an insoluble scum, and forms mineral deposits in pipes and hot water heaters. Water's dissolving ability makes it vital as an industrial material. Industry needs it as a solvent for a wide range of chemical reactions. Most of the water industry uses is discharged back into the environment, but before wastewater can be returned to a river or lake, it first has to be cleaned. Treatment plants hold dirty water in settling tanks so large particles can sink to the bottom. Bacteria are then introduced to digest the remaining organic materials. Proper treatment removes enough contaminants so that the water can be safely returned to the environment. But not all wastewater is properly treated, and undesirable substances still get into lakes and rivers, the main source of our drinking water. Further problems arise from leaking storage tanks and chemical dumps. Some of these substances are suspected carcinogens, which can cause cancer. So Senator David Durenberger has authored legislation to control carcinogenic contaminants that had been unregulated.
This is a large group of chemicals whose presence in our water supply caused us deep concern. As our ability to diagnose, detect becomes more refined, our knowledge and our understanding of the potential danger also expanded.
The federal government has set limits on the levels of such chemicals. But critics argue that the limits are stricter than what's needed to protect our health. Geraldine Cox is a vice president of the Chemical Manufacturers Association.
I think just because a material is there doesn't mean it's harmful. I mean, today I know that I ate carcinogens. I ate mushrooms with my omelet this morning. I had basil with the omelet. At lunch I had a hamburger. And all of those have known carcinogens. Am I afraid? No, I ate them.
All chemicals are toxic at some level. The open question is what levels pose unacceptable health risks. Contaminants in drinking water are trapped with chemicals and filtered out by hard coal and sand. The last treatment step is disinfection to kill bacteria. That's usually done with chlorine, or in some cases with ozone gas bubbled through the water. Disinfection is the main reason most waterborne diseases have been eliminated in this country. The water is then tested to make sure it meets government standards for cleanliness. But even the most modern treatments don't remove everything, and that's where the argument lies. Just how clean must our water be before it's considered safe? Modern analytical instruments can detect concentrations lower than 1 part of chemical in 1 billion parts of water. The limit for the chemical benzene, for example, is 5 parts per billion. Should we play it safe and set limits at these low concentrations or even lower? Or could we set them higher without any additional danger?
We have learned things repeatedly that tell us that our standards have been too lax. Lead, to me, is the best example, at least from my experience here over the last few years with lead. We used to tolerate some incredibly high amount of lead in water and in the air, but today we have banned lead from our gasoline. We are working on lead as one of the incredibly difficult problems in our drinking water system, and we've reduced or we've increased the standards for lead very substantially on the basis of new knowledge.
I think the criteria that we're using are the right ones. I think we need to be a little more realistic in setting the levels that we're dealing with. The goals for a carcinogen in drinking water are 0. But in some cases, that may actually increase the risk of cancer. I'll give you an example, selenium. Selenium is a known carcinogen based on laboratory studies. But yet, if water doesn't have a certain amount of selenium, people drinking that water actually have a higher incidence of cancer. So at low levels, it's an anti-carcinogen. At high levels, it's a carcinogen.
About everything we deal with in terms of the quality of drinking water has to do with chemists and chemistry. Our wonderful chemists have created these problems for us. Our wonderful chemists are hard at work in helping us detect and define these problems, and they're also being asked to help us solve these problems.
There have been contaminated wells, there have been hazardous waste sites contaminating material, and there have been releases of materials that shouldn't have gotten into the environment. That's all behind us. We are working very hard to clean up the environment, to reduce our emissions, to reduce the amount of contaminants. We have a responsibility to work to protect the environment and the health of people around us, but so does everyone.
Controversy about drinking water will continue. Hard choices will have to be made about acceptable levels of contamination. For new detection methods are bound to uncover more potentially toxic substances. Yet there is optimism. The quality of our water will improve because of a science that is responsible and creative, and because of a public that is well informed and active. To review, water's unusual characteristics set it apart from all other substances. Based on its molecular mass, it should be a gas, yet it's a liquid at normal temperatures. Its solid form is less dense than the liquid, and it's able to dissolve a wide range of other substances, including the vital chemicals needed for life and those used in many industrial reactions. The water molecule has partial positive charges at one end and a partial negative charge at the other. So it can form hydrogen bonds with itself and with many other substances. Water's properties make it vulnerable to contamination from industry and human waste. These contaminants have to be removed from wastewater before it's returned to the environment, and from drinking water before we put it into our bodies.
Why water in the laboratories, in our bodies? Well, first of all, a liquid is best, better than a gas or a solid for transporting matter or running a chemical reaction. A gas is too dispersed. It's difficult to get anything transported with a gas. And a solid is rigid. It's difficult to mix liquids and gases with it. A liquid is just right. It's movable, deformable, and it's no wonder that there are slurries and solutions running down the pipelines of our factories, just as there are in our bodies, in arteries, in veins, in the intercellular space. Okay, so a liquid. But why water? Well, water is the universal solvent. It dissolves ionic solids, transporting through our body sodium, potassium, phosphate, and it also dissolves non-ionic molecules, sugars, alcohols, and acids. Water is also attuned to the temperature of the planet. It is a liquid under most normal conditions, a solid or gas at the extremes. Waters teeming with life cover 70% of this world. Perhaps we should have called this planet not Earth, but ocean.
Funding for this program was provided by the Annenberg CPB project.
Additional funding provided by the people of Dow, the company that lets you do great things. The 8,000 scientists of the Eastman Kodak Company. The Exxon Education Foundation on behalf of Exxon scientists. And